There is my formula discretized form. It's not even so bad. My claim here, and it's going to be almost the claim all the time, is that this is just Ax equal to B. Just that we have to figure out what X is and what B is and what A is. Okay? All right. Now remember, once we kind of figure out how to do this thing, remember that this A, let's talk about how big A is going to get. If I chop it up into 100 points here and 100 points there, how many total grid points do I have? Right? So 10,000. Right? So, and that's not even chopping it up very much. 100 by 100 is it's not that big a deal. So you have 10,000 equations that you have to solve simultaneously. Okay? Now, when I started teaching this class in 2001 or something like this, right? 2001, I started teaching this. Back then, if you actually had a laptop, you couldn't really do this very easily on there. You do a 16 by 16, and maybe you could make it work in half hour. So you'd come to my office hours, you'd start it going. It'd sit there, thinking. And then what happened was this evolution of computing time, right? So nowadays, you could just throw it on your simple laptop that's not even an airbook like mine. And it'll still compute it out, and it will do it pretty fast. Okay? You can even do like 256 by 256. But think about what you're doing now. You're solving tens of thousands of equations all simultaneously. And you don't even think about it. This is the danger of computing, by the way. Because you kind of, it's so easy to do now sometimes that you kind of like you just do it. And you're like, oh, yeah, I could do that. I don't even think. There's the danger. All right. But this is what we're going after. We're going after pretty big matrices and codes. So you've got to line everything up right at the beginning. Everything. Remember, you're the secretary of this code. And if you don't get that part right, it's over. Okay, so there it is. It's a big A equal to B. And there's your equation. So let's figure out how we want to arrange the data. And by the way, what are we trying to solve for in this? We're trying to solve for a vector. Let's call this vector psi. And this will be our X that we're going to solve for. So we have to figure out how we're going to arrange our data. Notice that this is a vector, and our data in some sense is naturally coming in a matrix like this, because it's got spatial locations, right, in both X and Y. So you've got to figure out how to arrange this. So what we're going to do is going to take all this vector of information and stack it to one giant vector. So here's what we're going to do. Let me stay consistent with the notes so we can make sure to get this. All right. So here is my giant vector of information. Are you ready? No. Good. All right. I have it here somewhere. There it is. OK. All right. Psi 1, 1, psi 1, 2, psi 1, 3, all the way to psi 1n. And on top of it, I'm going to stack psi 2, 1, psi 2, 2, all the way to psi 2n. All the way to psi n1, psi n2, all the way to psi nn. There is my stacking of what I got to solve for. I got to put everything as this big, giant matrix, or vector, sorry. It's a really skinny matrix. Okay? So I need to solve for this. I've arranged the data in a certain way, and you see what I did here, right? I just took all these slices and I just stacked them up on top of each other. That's how I'm going to organize it. By the way, you can do it any way you want. Okay? You're the master of your code. Okay? You dominate your code. A lot of you don't know that yet. You're still trying to your code is manhandling you in your homework. So you got to get on that, drop some forearms on it, tell it what it's supposed to be, and then do it. Okay? Always understand you're the master of the code, so you get to do what you need. And I just picked this as a way to do it. You could have done it, started from here. You could have stacked it this way. You could have, it's your code. Okay? But whatever way you choose to do this, make sure you just stay consistent. Okay? That's the most important thing. Now, given that I have this piece of information about how I've stacked stuff, what's the right-hand side? So somehow the B vector here is what I already know. B is what I know, and here's what it is. B is going to be delta squared times the vorticity. Okay? And the vorticity we're going to stack the same way. At every point, I have a vorticity value. Remember, we're going to specify it initially to be something at time 0, and same thing. We stack it the exact same way. Okay? This is the easy part. Now comes the A matrix. Okay? The A matrix, okay, I'm gonna predict the future. Ready? Watch me. Okay. Yes. You'll be frustrated. This is the hardest part of this thing, is seeing this. You're going to have to piece it together. Now let's figure out how to do this. We're going to walk through how would you construct the matrix A that does this 2 derivatives in x, 2 derivatives in y, and it connects it to the way I've stacked my information. Okay? All right. This is the you will spend time pencil and paper, and you're going to make some other matrices like this, and this is where you're going to pull some hair out. Just be thankful you have some. I'm getting old enough where it's like, all right, I should stop doing that. All right, so you ready? Let's build a matrix A, and it's big. That matrix A, by the way, if those vectors are each 10,000 by 1, this matrix A is a 10,000 by 10,000 matrix. That's not even that big. Okay? It's big by standards of, if you did linear algebra, you're like just working with 2 by 2s and 3 by 3s, and you may think, man, dude, I'm doing 10,000 by 10,000. But really, by computational standards, that's not big at all. You want to go oftentimes a lot bigger. This is a 2D problem. You go to 3D. Think about this. If you go to 3D, it's another direction you've got to slice up. So your 10,000 by 10,000 now becomes, right? You had 2 more zeros there. So you got a million by million for a simple 3D problem where you cut up 100 by 100 by 100. So you see the problem that Boeing has? Okay? You want to do full CFD on a mock-up of an airplane? It's still a lot cheaper than building it, but this is not cheap. And so your ability to solve this quickly becomes very important. Okay? Remember, a lot of right answers to this, but your ultimate goal is to evaluate the fastest answer, the most accurate and most efficient. Okay? So you get the quick turnaround time. All right, let's talk about this matrix A. It is being multiplied by the vector x, which is this psi. Let me write them over here. Psi 1, 1, psi 1, 2, psi 1, 3. And you know what? I'm going to go all the way to psi 1, 4. We'll stop there. We'll assume that we cut it up into 5 spots. Remember, the last one is periodic boundary, so the last one is the same as the first. And then psi 2, 1, psi 2, 2, psi 2, 3, psi 2, 4. Start with that for now. And let's ask the following question. This first line of the matrix corresponds to the equation for when n equals 1 and m equals 1. So let's go to that point, psi 1, 1, and ask the following question. What's going on here? Who are the neighbors of this guy? Well, it has a neighbor here, psi 2, 1. Has a neighbor there, psi 1, 2. Right? So I got to put those in. And by the way, how do they relate to these neighbors? The nice thing about this is if I'm at this point, let's take a look at the formula over here. This formula tells me if I'm at a certain point, I have minus 4 of myself. Okay? And then I have 1 of all my neighbors. Okay? So first of all, if you're at that point, you have minus 4 of yourself. And then you have 1 of psi 1, 2. Where does psi 1, 2 sit over here? Oh, that's the next term over. So when I multiply this, it's just right there. Where is psi 2, 1? Well, now I have to go 1, 2, 3, 4, 5. Now I'm going to do some foreshadowing. A little box of 4 by 4. Okay? Because remember, everything's going to be broken up in segments of 4. And now this is the psi 2, 1 spot. What's the weighting you have with that? 1. Who are the other neighbors? Well, now, now if you look at here, your neighbor is over here, but there's no neighbor over here. But remember, this point is the same as this point. So this would be the fifth point. So the point it relies on is this one. And the point it relies on in this neighbor is over here. This point over here would be psi 1, 4. This point over here is psi 4, 1, if we chop it up with 5 slices. So where is psi 4, 1? Where is psi 1, 4? So psi 1, 4, actually, it's fourth in. So actually, I don't have a 0 there. I have a 1. Psi 4, 1 is way down here. The last 4 components are psi 4, 1, psi 4, 2, psi 4, 3, psi 4, 4. Psi 4, 1 is the fourth in from the end. Everything else is 0 in that row. Okay? We got one equation in. Are you feeling good? No, see? All right. Maybe with 2 equations you'll feel awesome. All right, so let's see here. We're going to start putting this in. You're going to start seeing a pattern. This is the most important thing. Okay? We're not going to go solve 10,000 of these and put 10,000 rows in. We're going to watch what the pattern tells us, and then just, boom, you're done. Okay? Second equation. Now we're going to solve for psi 1, 2. Psi 1, 2 is now here. Let me do this in red. Minus 4 of itself. Who are the neighbors? 1, 2, 3, and this one over there. Okay? So you have all your neighbors. So your neighbor down here, psi 1, 1. Your neighbor up here, psi 1, 3. And you're at psi 1, 2. So if you look at where you are, now you're in the second row. Psi 1, 2, you have minus 4 of yourself. You have one of your psi 1, 1 neighbor and one of your psi 1, 3. So psi 1, 1 is above you, psi 1, 3 is below you. So when you lay it across, when you do this matrix multiplication, psi 1, 1 multiplies here by 1, here by 1. And then you're going to have a 0. And the only term left over is way over on the other side. And this term here is psi 4, 2. Psi 4, 2 is all the way down here. So it's, all right? Oh, yeah. There. Great, thanks. So Gar's good? Let's go to the next equation. Psi 1, 3. I'm going to run out of pink colors, but that's okay. Let's just do this one here. Neighbor, 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 neighbor. So you got all your neighbors there. You've got to calculate what they look like. So you have minus 4 of yourself. Now you're at psi 1, 3. You have one of each of your neighbors, top and bottom. Then you have psi 2, 3. Then you have the other side, which is psi 4, 3. See the pattern that's starting to emerge here? So what you get is the following. Let me just try to write. So you get, notice what happens here. You have ones along this structure here that just continues. Okay? You have ones over here. But by the way, when you get to this row, these ones will go across. It's periodic. These ones will continue over here. So you have 1, 1. By the way, when this goes down here, when it hits this edge, that last cell of ones that would be over here gets shifted over there. And then all down the diagonal, you have minus 4. But notice what happens here. You have 1, 1, 1, 0, 1, 1, 1, and then a 0. This is the pattern of the ones there. And then your periodic boundary condition. So I'm going to just draw what this whole thing looks like. And part of your job is to actually work this, like convince yourself that this is right. Okay? And you're going to do it for 2 other matrices. Okay? You're going to have to get your head around it, because if you get any one of this, so it's 10,000 by 10,000 matrix, let's say. If any single one of those elements is wrong, score later. What do you think it's going to say? Squirrel is going to say, sorry. Dude, try it again. Okay, so just remember, you had 10,000 things to get right. The nice thing is mostly it's zeros. So it's already kind of a help for you. All right? So, but if I do this whole matrix out to this form, I'm going to show you a matrix here. Let's make a little matrix called B1. The rest are zeros. Oh, sorry. Can't fit in all these zeros. Okay, and then a 0 here, and then a 0 there. Okay, that's a little submatrix. All right? And then I'll make the little identity matrix, which is 1s down the diagonal, 0 everybody else. Then that matrix A looks like the following. B1, 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 all the way down. And then you have identity down this side, identity down this side, identity here, identity there. Okay? You're going to convince yourself of this. You have to get this right. But this matrix is very powerful. What this matrix does, you take a vector in 2 dimensions, you multiply by this, it takes 2 derivatives in x, 2 derivatives in y, gives you out the answer. That's what that matrix does. It solves the Laplacian for you. It gives you a Laplacian. Laplacian shows up everywhere. And you just have a vector or matrix now that just will give it to you computationally. With the assumption that you have periodic boundaries, by the way. That's why you have these structures on the end here. It's all due to periodic boundaries. That's why you have these 1s on the corner, all due to periodic boundaries. Okay? But notice, one extremely crucial thing about this matrix. This thing could be 10,000 by 10,000. Okay? That's a lot. That's a lot of information, right? This is a huge matrix. You could have this thing be. But how many? It's almost all zeros. You better take advantage of that. Okay? So it's sparse. This is what a sparse matrix is, one that has mostly zero structure in it, and then just has some stuff in there. How many diagonals actually matter? I have one diagonal here, 2, 3, 4, 5, 6, 7, 8, 9. 9 diagonals. So if it was a 10,000 by 10,000 matrix, I'd be concerned. It's huge. But really, all I got to store is 9 times 10,000 to represent that matrix. Okay? There is a limit in MATLAB when you use it. If you try to build really huge matrices, basically you can go up to the size until whatever your memory is on your chip. And as soon as you go above it, it says, sorry, we're done for the day. Okay? Right? So there's a danger there. Obviously, you get too big. And you might say, well, I can just buy more memory. Right? Because that is a solution now. Memory is not so expensive. But if you're going to do a 2D, 3D problem, look, you can't play that game. You can't afford the kind of memory it's going to cost you to really go to high resolution. It's expensive. Okay? Plus, why would you, what you've got to do is figure out how to represent this information in some compact way. And that's what we're going to work on doing. So it's not just speed, but it's also trying to keep stuff out of the memory cache that's sitting there. If you just load that up with information, you got no place else to work. Now, if you were to do this in Fortran or C, what Fortran and C would say, hey, the memory's full. I'll start using your hard drive for space. If you want to take 1,000,000 years to do a computation, that's what you want to do. Okay? As soon as you start accessing hard drive and start storing stuff over there, you're in trouble. You kind of want everything to happen on that processor.